their functional properties, right? So this is more or less just to show you the diversity of lipids, and that's why this class is one of the tougher classes really to understand fully, because there are so many variations and differences. The one unifying feature is they're all fairly hydrophobic. They all contain a lot of hydrocarbons, but you can see that there is a lot of diversity when we go from the fatty acids to the sterols to basically what we can call other lipids. Okay. So here's some examples of some very unique lipids. These are polyketides. These are bioactive molecules. These are often what are found in nature. They go to these plants and they extract these molecules, these biomolecules, and they're often very good anti-cancer agents. They're very good medicines, okay, or treatment agents. So things like erythromycin, right here, this is an antibiotic. Amphotericin B is an antifungicidal molecule, and levastatin, statin, right? Statins are used for controlling blood pressure, right? And these molecules are derived, they're found in nature. And so what people want to do is they want to understand these kinds of lipids really well because they have such value to human health, okay? But you see how, look at these. These are just beautiful structures, aren't they? These are just look at all the different chiral centers, right? And if you were to change one chiral center in this, you would totally change its properties. So this is an antifungal. If I were to say change this hydroxyl and move it to, if this is R configuration to the S configuration, completely change it. And just imagine how difficult this would be to synthesize synthetically. This is done regularly in cells. They have a machinery that can specifically synthesize these elaborate structures. Look at how many chiral centers there are in this thing. Okay? And this is what Dr. Butler studied as a graduate student. How do I take structures like these and synthetically synthesize them? Not with enzymes, but how do I retrosynthetically break it down and do organic chemical reactions to build these? And what you might understand just by looking at these, it's very daunting. And yet, biochemistry does this effortlessly. And it's amazing. And if you change one chiral center, it completely obliterates its bioactivity. It's just amazing. Okay, so let's just summarize what we've talked about. This will finish up our chapter 10. So lipids are structurally and functionally diverse class of molecules that are poorly soluble in water. And if you've noticed as I've talked, we often say that there are carrier proteins that are involved with them, right? Because they are soluble, but to make them more soluble, we often associate them with a protein carrier. Triacylglycerols are the main storage lipids. We talked about that. We talked about sphingolipids, which are important components of the membrane. We talked about sphingolipids, which are important for cell recognition, right? They're found on the exterior of the cell membrane, and these are often glycosylated, right? And so that's where you get like your differences in blood types that we've talked about. It's because there's a sphingolipid with specific sugars as head groups. Okay? Cholesterol, we should transition into that, and that's a major component of hormones and the membrane, specifically for cholesterol, but these hormones are derivatives of that steroid ring of cholesterol, and they are synthesized from cholesterol. Okay? Some lipids carry signals from cell to cell, some from tissue to tissue. We really didn't get into that, but we have these other class of molecules, right, that can signal, and depending on their structure and what they associate with, they can influence signaling between cells or between tissues. So there's a whole range of function that they can carry out in signaling. Okay. So if you want to Yeah, we should have probably had you do this before, but you should have read chapter 11 to be prepared. I'm guessing you're reading more on the topics for the exam on Thursday, right? So we'll not worry about that. Catch up in reading, and then look over these problems. These should be helpful, okay, in understanding this material more thoroughly. I would know, I want you really to know that ring, and cholesterol is key. Okay, so cholesterol is key because everything is derived from cholesterol. So you need to know cholesterol. Some of the ones that would be important for you to know are things like testosterone, aldosterone. These are very important. You don't need to know all of them. What I really want you guys to know, though, is very much cholesterol. And then just know, how does it get converted, physically? What's the difference between that and a steroid, right? Cleavage of, get rid of that long chain fatty acid, and then you have these differential oxygenation, hydroxylation, right? So I think at this point, what we need to know is cholesterol for sure, and then maybe testosterone, know that one. But know how it becomes these signaling molecules. Does that clarify everything? So no cholesterol, no testosterone as an example of a steroid. Okay? And then just know how those differences come about, right? That it's basically cholesterol has that alkyl chain removed, and then we get differential hydroxylation or oxygenation, right, that leads to those new molecules.
I can take immunology or something.
So,
like some kind of
that finishes our introduction, right? Every time we introduce a new molecule, it's kind of, here's this kind of molecule, here's that kind of molecule, here's that kind of molecule. Now, what we're going to get into now is what's the more functional understanding of basically phospholipids and the sphingolipids, how are they involved in the cell? And we're not going to look at signaling molecules. We're going to look at the ones that are components of cell membranes. Okay? So now that we've learned about the different types of structures and the different types of molecules, we'll see how do they come together to build up, right, some kind of functional component of the cell. And those we'll be specifically looking at biological membranes. So those fatty acid containing molecules, right, the glycerophospholipids, the sphingolipids, and also cholesterol. And we'll see how are these come together, what are the interactions involved that lead to a very important component of the cell membrane. And then the question is, okay, we have this very hydrophobic membrane, right, that we'll talk about. How are things transported across that? Because cells, right, are open containers, semi-permeable, right? We have to be able to take in nutrients from the outside so that we can use them as fuels, right? And so we are separated by this membrane, right, this lipid membrane. So we want to understand, well, how do things get through that? Because it's very hydrophobic. Okay, so just an overview. We'll brush right through the lipids because we just finished these up. We'll talk a little bit about this membrane structure, okay? Its dynamics and its makeup so we can understand the physical properties of the cell membrane, what it's made up of, okay? And then we will end up with talking about transport of molecules across this membrane, right? Because it has a unique property about it that it's semi-permeable. We need to know, well, how do things get in? Okay, so remember, here's our list of structurally diverse lipids, right? We've got the fatty acid-containing lipids shown here. And this is a phospholipid, right? And then we have cholesterol, which are these ring structures, very different in structure, right, than the fatty acids. And then we have these more signaling type molecules or functional type molecules that also have these kind of conjugated ring systems. So organic molecules that are characterized by low solubility, we talked about this last time. We talked about how we can classify lipids into two groups, basically fatty acid containing and non-fatty acid containing. We talked about storage, right, which is pretty straightforward. We talked about adipose tissue and how fats are stored there. But the functional ones that we're going to talk about today are over here in the membrane lipids. We'll focus on these phospholipid, glycolipid types, right? So we talked about conformation of fatty acids and how you can have unsaturated, right, that have these kinks. And they're all cis form, right? The natural form of the unsaturated fatty acids is always kinked, right? Okay, and the saturated version is very linear, right? This leads to different physical properties, right? The saturated fatty acids can line up and act very efficiently through van der Waals contact, through hydrophobic effect, right? Whereas the kinking, right, in the unsaturated fats leads to greater disorder, right? They cannot effectively pack against one another, so these are more fluid. They're more they're typically involved with liquids, right? We talked about unsaturated fats are typically lipids, and these fats, right, these solid fats typically contain a lot of saturated fats because they can stack on one another, and that intermolecular interaction between these chains is very, very strong, right, because of these effective packing and chemical interactions. Okay, we talked about this major class, glycerophospholipids, right, has a polar phosphate head group, and then to the other hydroxyls of the glycerol component, we have fatty chains that can be added, right, and we showed a typical structure right here. Right? Typically in this 3 position, we have saturated fatty acids, right, like palmitic acid, or in the 2 position, typically we get our unsaturated fatty acids. Then we talked about polar head groups, ethanolamine, choline, we can have amino acids, serine, glycerol, and how attachment of these to that phosphate head group, right, completely changes its chemical properties, right? We go from having just a phosphate group, now we have a charged amino group, right? A tertiary or quaternary amine, right? And then what do we have here? Serine, glycerol, these have very, very different functionality, right? And so these can be used to modulate that lipid. Right? We talked about sphingolipids, right? How it has this sphingosine backbone. And again, we have different types of head groups. Largely, though, we have sugars that are involved in their head groups because they make up the exterior of the cell membrane, right? These are involved in recognition with other proteins, recognitions between cells, and sphingolipids are the major component of the exterior. Okay, so that's the review, right? That we know about these molecules, okay, how are they involved in interactions, or what interactions are they involved in the cell, okay, to make up the membrane? That's really what we're going to be looking at. So there are different types of structures that can form from these fatty acid lipids, okay? If we have just an individual fatty acid, right, that has this kind of shape. So determining what kinds of structures form, you can determine just by looking at the shape, right? Shape, how many of you have ever played with Legos, right? Legos. And what you build depends on the shape of the building block, right? And this is how all of life works, if you want to boil it down in a nutshell. All of life is arranged by the complementary of the building blocks, the shape, the interactions that can form between those building blocks that tie them all together. Okay? And this is the case for lipids, for why the membrane forms. So if we have just the fatty acid, that's shown here, right? This is the polar head, this is the fatty tail. Okay? And if you have something like that, it forms more of a wedge shape. And so what kinds of structures form from wedge shapes? Well, if you're in water, right, this polar head will interact with water. But this fatty acid tail will not interact with water, right? It's hydrophobic. So what happens is they pack in the most efficient manner, and they make things like micelles. Micelles have an exterior that's exposed to water, okay, and an hydrophobic interior that effectively gets these hydrophobic tails away from the water and efficiently packs together. That's a micelle, okay? So that's one of the structures that can form. That's formed from these very simple carboxylic acid-containing, right, long-chain fatty acid. Okay, now when we move up to phospholipids, right, or sphingolipids, now we have two chains that hang off of glycerol, right, and have a polar head group. So their structure is very different, just kind of from a schematic point of view. They have a more tubular structure, a more cylindrical shaped structure. And what kinds of things can be built up from cylindrical building blocks? Well, things like lipid bilayers. Okay? So we can see how they can form two phases. Each phase is known as a leaflet. Okay? And they can pack within that, where each leaflet has its tails that pack against one another. And we have two sides, because remember, water's all around, right? So water's going to be up here, down here, and it's effectively keeping these fatty acid tails away from each other. And it's basically because of this shape function, right? They're trying to find the most effective way to pack with one another. And this is what will form. You can also have things like vesicles form with these kinds